Hello everybody. I would like to do a short pre-lecture on molecular, ionic, and net ionic equations for both precipitation and acid-base reactions. Okay, so really focus on these. We will practice one more of each of these in class, and plus there's more to practice in the homework, more to practice in the review quiz, and so on. But really focus on these. There's a lot of steps to follow. And students tend to struggle with these because you really have to, not only do you have a lot of little pieces to put together, but you need to put them together in the right order. Okay, so let's just start with precipitation reactions. Now for precipitation reactions, we're going to need to use the solubility table just to see if something will precipitate from solution. Now you might have some reactions where you mix two salt solutions together and no precipitate forms. Okay, so be wary of that. But in general on these, there will be a precipitate. So here are the rules for writing out a molecular equation. So remember, we're going to write molecular, ionic, and net ionic. But we need to start with the molecular. Okay, so we're going to start with what's called the molecular equation. Everything is going to be shown as molecules. The ionic equation, as the name might express to you, we're going to show things as ions that exist predominantly as ions in solution. And so let's take a look at an example here. So here we have these two salt solutions, magnesium sulfate, this guy right here, and strontium chloride. Okay. Now, I show that these are soluble salts because I write AQ after them. That's to indicate that they are dissolved in water and hydrated by water molecules, surrounded by water molecules. You should check your table and see that most sulfates are soluble. There are some exceptions, but magnesium sulfate is not one of them. And most chlorides are soluble. Few exceptions that are insoluble, but not strontium chloride. Okay, so those are soluble. But this AQ here indicates that these are soluble salts. All right, so let's follow the rules. Assign charges to cations and anions of the reactants. Now, I'm not going to keep scrolling back and forth between this table, but you should have your book open. You should be looking at one of these solubility tables. I will give you one of these on the quiz, and you'll see that sulfate is -2 in that table. Okay, now remember, sulfate is this whole group, SO4 grouped together. To balance that charge, magnesium must be 2+. Okay, so these are neutral salts. Charge must balance. All right. Now, as we go on in this course, we'll figure out more about why these charges happen. If you're curious about magnesium, the main group elements, groups 1 and 2, and then 3 through 8, they will tend to gain, lose, or share electrons to achieve a noble gas configuration. So if magnesium loses 2 electrons, okay, it will form the electron configuration of the noble gas neon. So take a look at that. But that's what we're going to head to. We're going to find more out later in the course where these electrons are, why magnesium loses 2 electrons typically. Okay. You will also notice in the table that chloride is -1. You could also look at the periodic table and see that the halogens are 1 away from the noble gases. They will tend to gain an electron when forming an ionic compound. So 2 times -1 for chloride must mean that strontium is +2. And you might notice that strontium is in the same family as magnesium. Kind of makes sense that it'll be +2. All right, assigning the charges is important because that will allow us to write the correct formulas of the products. So what we're going to do, and since I have a mess here already, I'm going to write in a different color. We're going to take, this is step 2 now, combine the cation of one salt with the anion of the other, and do the same thing for the other salt, cation with anion. And we're going to get 2 products. If I can get my blue pen again, I'm not hitting the right thing. One product will be, and bring your charges over, magnesium 2+ with chloride, that's one product. And the other is strontium 2+ with sulfate 2-. Okay? So, step 2. So we've done step 1, assign charges to cations and anions of the reactants. We've now combined the cation of one salt with the anion of the other, and vice versa. Now we need to do step 3, and it's crucial that you get the right formulas before you balance. Students quite often want to balance first when they don't have the correct formulas. If you don't have the correct formulas of your product, you're not going to get the correct balanced equation. So we write the correct formulas by balancing charge. These compounds, these salts, are neutral. And so since magnesium is 2+, I'm going to need 2 chloride ions to balance that +2 charge. 2 times -1, that's -2, to balance that +2. Strontium and sulfate are already balanced, so we're done with that one. Okay, step 3 is done. Correct formulas of products before balancing. Now we balance the equation with coefficients, step 4. All right, so let's take a look at what we have. Wow, balanced already. Okay, I didn't intend that. I just made up a problem, and I was hoping that we'd have to actually balance this, but it looks like we're done. We have 2 chlorides here, 2 chlorides there, 1 sulfate, 1 magnesium, 1 strontium. We'll definitely work one in class where you do have to balance it. Okay, it's going to be the one we'll do in class, it's going to be a little bit more challenging than this. All right, it's already balanced. Good to go. Step 5, check solubility rules. So I'm going to scroll back up. Chlorides, most chlorides are soluble. Okay, here's our rule. Chlorides tend to be soluble. Here are the only exceptions. Okay, and magnesium 2+ is not on that list. Okay, so magnesium chloride is soluble, so we're going to write AQ after it to indicate that it's dissolved in water. It's hydrated by water. What about sulfates? Most sulfates are soluble, but there are some insoluble exceptions, and one of those is when strontium 2+ is combined with sulfate. Okay, so remember at the top part of this table, soluble compounds, these exceptions are insoluble. Okay, so strontium sulfate will be insoluble. It will come out of solution as a solid. We say it precipitates from solution, and that will be a solid. Okay, not so bad. Now, that kind of is our molecular equation, but we have these charges and everything all over the place. When we write out our molecular, we want it to look a lot cleaner than that. So let's rewrite this without the charges. So rewrite our molecular equation. So it will be magnesium sulfate in solution plus strontium chloride in solution, magnesium chloride in solution, and then strontium sulfate will be a solid. There you go. There's your molecular equation. A lot of work. There's a lot of places that you can make mistakes. So really focus on these. Okay? The steps make sense. As you're practicing these and you're doing these on the homework, keep those steps in front of you. Write them down and follow them. Follow them in order. All right. Now, ionic. What we assume for an ionic equation is soluble salts completely dissociate into ions, okay, in solution. So they don't actually exist as a molecule, which actually isn't right for an ionic compound to call it a molecule, but let's call them molecules. They're actually going to be ripped apart. The water molecules are going to surround each ion and break that ion apart, break that salt apart, break that ionic bond. Okay? So anything that has an AQ after it, those are soluble salts, and we're going to break them apart into their component ions. So that's why it's also helpful, look back up at the top, that you've assigned the charge, because we're going to break them apart into those component ions. Okay? So the ionic, magnesium sulfate is soluble. Magnesium sulfate is composed of magnesium 2+, and again, we need to write AQ because that shows that magnesium 2+ is surrounded, that cation is surrounded by water molecules, and sulfate. Okay, so that salt exists as separated cations and anions. It's dissolved and dissociated. Okay, dissociate means break apart into these ions. Same thing for strontium chloride. Strontium 2+, look at your charges that we assigned above. And now you'll notice this subscript of 2. we take the coefficient, which is 1, times the subscript to get 2 chloride ions in solution. Okay? What about magnesium chloride? Soluble. So it's going to dissociate into ions. Magnesium 2 plus in solution. And again, coefficient times subscript, 2 chlorides. Now, one word of caution. Be careful. You might be saying, well, doesn't sulfate have a subscript of 4? No, remember that's SO4. The sulfate subscript is actually 1. There's 1 sulfate for 1 magnesium. Okay, watch for that. Students tend to like to break apart their polyatomic anions. Keep those together. And the last thing from our molecular is that precipitate. That is going to exist as the solid with the cation and anion combined together. So we write that together. It is not soluble. It does not dissociate to any great extent into ions. It will exist predominantly as the solid. And that is our ionic equation. Anything that exists as ions in solution, we show it that way. It's a better representation of what's really going on in solution. Okay, the soluble salts break apart into ions. The insoluble salt comes out as a solid. And the last step in this is the net ionic. What is really reacting? Okay, there are some things that are called spectator ions. And the name makes sense. They are there, but they're spectators. They're just watching what's going on. They're not participating. They are not reacting. And they're pretty easy to pick out because they will look the same on the left and the right, on the reactants and product side of the reaction. So take a look. We have magnesium ions there. Let me get a different color so I can highlight this better. We have magnesium 2 plus, magnesium 2 plus. Nothing changed. That's a spectator. It's just hanging out in solution, not doing anything. Chloride. Chloride. Other spectator ions. Watching the action, not participating in the game. So the real reaction, and this shouldn't surprise you, strontium 2 plus is combining with sulfate to produce that precipitate, strontium sulfate. That is the net ionic. That's the real reaction that's going on in solution. And so we can write out our net ionic. And I like to write the cation first. If you don't, that's okay. We typically in the salt write the cation before the anion. So when I write my net ionic, I'm going to switch these up. Strontium 2 plus, sulfate 2 minus. Those are the two ions that are combining to produce our precipitate. There you go. Okay. Now you can see, if I timed myself correctly, this problem took about 13 minutes. All right. That's why we're only going to work one more of these in class. So really focus on this one. Try to get this down. We're going to work a harder example in class. You will have plenty of chances to practice on the homework this week and the quiz this week. Okay. So, but really look through, look at the steps, make sure you understand the process for these. All right. Precipitation. Now, if you understand the process for precipitation, acid-base is kind of the same, but a little bit different. Okay, the reaction is a little bit different, but the molecular, ionic, net ionic, and the way we approach it is the same. Now, we've talked about already, how do you recognize strong acids and strong bases? You need to know your 6 strong acids, and nitric acid, HNO3, is one of your 6 strong acids. Know that list that I gave you. Soluble hydroxide salts are strong bases. Look at the solubility rules. Barium hydroxide is soluble, so this is a strong base. So we are reacting a strong acid with a strong base. We'll talk about what that strong means in just a minute. We've kind of talked about it already, but we'll re-emphasize what we mean by a strong acid and a strong base. All right, so we do want to assign charges. The acid has an H+. You can look at your solubility table, although you could guess that because it's H+, nitrate is -1. But look at the solubility table, it'll show nitrate is -1. Okay. Strong bases contain hydroxide, OH-. That's also in the solubility table. We have 2 hydroxides at -1. That must mean that barium is +2. All right. Barium is also an alkaline earth metal. If it loses 2 electrons, it will have a noble gas electron configuration. We will do more with that as we go on. So same thing, we assign charges first. We know the acid has H+, the base has OH-. That kind of makes our job a little bit easier. Now, H+, step 2. H+ from the acid combines with hydroxide from the base to produce one of the products, water. So let's take our arrows here, cation with anion. So it's the same, but it's always going to be in an acid-base reaction, H+ and OH- to produce H2O. Now, water is a pure substance. That's our solvent, in effect. So it's not aqueous. It is a pure liquid. So we write L for water. All right? And then the other product is going to be taking the other cation, the cation from the base, with the anion from the acid, to produce a salt. So you've probably heard this before. Acid plus base produces salt and water. That's your typical acid-base neutralization reaction. And we'll talk about why it's called neutralization in just a minute. So our other product is the salt. Now, just like the precipitation, we do have to write the correct formula for our salt based on charge. So carry your charges over barium 2+, nitrate -1. Remember that negative charge on nitrate applies to the whole grouping of those atoms. The nitrogen and the 3 oxygens together have a -1 charge. Barium is 2+. We're going to need 2 nitrates to balance that +2 charge of barium. 2 times -1 to balance that +2. All right. So we've combined H+ from the acid with hydroxide from the base to produce water. We then combine the cation with the anion to produce the salt. I actually jumped to step 3. I did step 3 already. Obtain the correct formula of salt by balancing charge. We know how to do that. Now we balance the equation with coefficients. And I think we actually do have to balance this one, which is good. So I would look at nitrate. I wouldn't look at it separately as N, nitrogen and oxygen. I would look at that I have 2 nitrates. I only have 1 nitrate on the left. So I'm going to need a coefficient of 2. Now the hydroxides get mingled into the water, so we're going to have to count the hydrogens separately here. So I have 2 hydrogens plus 2 hydrogens, that's 4. So I'm going to need a 2 here, so I have 4 hydrogens on each side. And what about my oxygens? Let's see, I have 6 in the nitrates and 2 more in the hydroxides. Yeah, so that looks balanced. So there we go. Not too hard to balance. We had to put a 2 in front of nitric acid, 2 in front of water. All right, so that is our molecular... Oh, one last thing. I forgot to check solubility rules. Usually you will not get a precipitate in an acid-base reaction. You will not. But you might double check. You will see that all nitrates are soluble. All nitrate salts are soluble. And so this we write AQ after to indicate that's a soluble salt. All right, we're going to clean up our molecular equation now. 2HNO3, aqueous. Strong acids and strong bases are soluble. Barium hydroxide, aqueous, going to 2H2O liquid, and barium nitrate, aqueous. All right, there you go. Cleaned up molecular equation. So the charges and all that up above is just to help us write out the correct equation. But when we write the molecular, we don't put the charges in it. All right, next step. Ionic. Strong acids, strong bases, completely ionize. Strong acids, strong bases, completely ionize. So just like soluble salts, as in the precipitation reaction above, we're going to break those apart completely into ions because that's how they predominantly exist in solution. So what we're going to do, and again, watch your charges. The subscript of hydrogen is 1, but we have a coefficient of 2. So we're going to get 2 hydrogen ions. Same thing for nitrate. Be careful. The subscript of nitrate is actually 1. There's only 1 NO3-, but we have a coefficient of 2. So 2 NO3-, 2 nitrates. Coefficient of 1 in front of barium hydroxide, so we have 1 barium ion. Again, look up at what we did in the example part up here to write the correct charges. We've already assigned the charges, remember? And then we have 1 times 2. Now, that subscript of 2 does apply to the hydroxide, so we have 2 hydroxides producing water. Does not ionize hardly at all. Does a teeny little bit, but predominantly exists as H2O molecules. And then what about our last substance over here? What is that? That is a soluble salt. Soluble salts completely dissociated ions. So we're going to break that apart as well. We have a barium ion, okay, and 1 times 2. And I apologize, I did not leave myself enough room, but hopefully you can read that. 2 nitrates. So there's our ionic equation. Sometimes I'll call it the complete ionic. Everything that exists as ions, strong acids, strong bases, soluble salts. Make sure you know that. Strong acids, strong bases, soluble salts will completely break apart into ions. Now, how do we transition to the net ionic? What do we eliminate? Spectator ions. What are our spectator ions? Nitrate. There's 2 of them there, 2 of them there. Barium ion, barium ion. No change. Hanging out in solution, having a great time, but not reacting. What is our real reaction when we mix a strong acid with a strong base? H plus from the acid. Okay. Remember one of the definitions of an acid? Acids donate hydrogen ion. Okay, there's the hydrogen ion that's donated. Bases do what? Accept a hydrogen ion. So the acid is donating the H+. The hydroxide of that strong base is accepting it. And what do we produce? Water. Okay. So H+ from the acid combines with hydroxide from the base to produce water. We've gone from we had an acidic acid, a low pH, if you know anything about the pH scale. We really won't do pH scale till next semester. But a low pH is acidic. We have a base that has a basic pH, a high pH. We mix them together and we form neutral water. Okay? Hence, this is called a neutralization reaction quite often. When we perform this reaction in the laboratory, we'll call it a titration, but in a titration, we're really neutralizing the acid with the base. Neutralization. Now, hopefully you're thinking what I'm thinking about how we balance equations. And we balance equations with what in terms of the coefficients? The smallest set of whole number coefficients, the smallest set. So while this equation is balanced, it would be more appropriate to write it as H plus OH minus to produce water. Okay, we divide each of the coefficients by 2, and then we reduce that to smaller whole number coefficients. And make sure you know this. This is, for a strong acid, strong base, this will always be the net ionic equation for a strong acid, strong base. Know this. Strong base reaction, neutralization reaction. Okay? Sorry, I kind of rushed that writing. It's pretty lame. But this is the net ionic equation for a strong acid, strong base reaction. H plus from the acid combines with hydroxide from the base, so H plus from the acid combines with hydroxide from the base to produce water. Neutralization reaction. That will always be the case for strong acid, strong base. You need to know that. All right. Longer than I wanted, I think. Probably 25 minutes. That's about usually what we essentially have to make up. This is a 4-credit class. We only meet in class 3 hours. So we really need to make up an hour. And by hour, an hour period is a 50-minute period at NAU. So 25 minutes for each pre-lecture. That's our 50 minutes that we lose each week. All right. So anyway, good luck with this. Practice this. You might want to practice some of these homework problems before class. We'll do one more precipitation, one more acid base, go through molecular ionic, net ionic, and then we will be moving on. So make sure you try to get a handle on this before class. All right, I will see you soon. Take care.